All right, hello folks. How we doing today? Okay, good. All right, so good to see you all out there. Oh, that's everybody because it's not just you. Let me go ahead and do them. I don't understand why for this type of quiz. I mean, I went in and looked, and I actually have to go to grades and hit submit, and you got to do it all at once. It's like you can't do it for just one person. You got to hit post grades, and I don't know. I mean, I don't know why it does that. Because I used to do little quizzes before and never had that issue. So I'm not sure why it does that. Maybe that's for everything. Because I've not used Canvas that much. But before I'd have some that I have to grade by hand, like maybe one or two problems. And maybe I just didn't notice that I was having to do that there. But that's why. So they should be there now. Okay, that should be done now. Yeah, they all have to be done at once. It's just the way that it works, evidently. Like I said, I don't know why I can't figure out how to do that on its own. All right. Anyway, we're going to continue on with stuff because we really probably ought to finish this by Thursday or by next Tuesday for sure. I think we shouldn't have no problem with it. But we're taking up with the remaining stuff here in chapter 8, 8.2, and 8.3. To just kind of take an overview of things, there's three different types of tasks. There's the one-tailed tasks, which are the first two from the left. The left tail task means the critical value is on the left, and the middle one is the right tail test, where it's on the right. So these are mirror images of one another. So you just got to handle them a little bit differently, because when you look up your area, you got to make sure that you got a negative z value for the left, and I'm sorry, critical value for your on the left, and it's going to be a positive one on the right. And then when you got the two-tailed test, remember you're splitting your alpha in two, and it's going to be evenly broken up, and you'll have a negative and a positive one. And so if it falls in any one of those critical regions, either the left, the right, or the two-tailed test in either the left or right, then you got enough evidence to reject. So as I had mentioned before, but maybe it's kind of hard to just say it, but this little chart just kind of shows you. Remember, the 0.05 is like the 1 minus 0.95. So this is very similar to the 95% confidence interval. And if you look at two tails down there, you'll notice that 1.96 is the same value for a confidence interval. Now, if you leave it all on one side, like with a left-tailed or right-tailed test, then it's 1.645, which is like the two-tailed 90% or 0.10. So just keep an eye out for that, because that can be a tad confusing. But for the mean, when we're talking about the mean, which is anything in 8.2 or 8.3, we're simply got to make sure that these assumptions are met. Simple random sample, which is basically most everything in the whole book. We got to assume that. because we don't have any control over it. Now, the sample size is large, which is greater than 30, or we know that we are dealing with an approximately normal distribution. Now, in chapter 7, we started with some that we looked at some that were small, like 15 or 16 or 8, and so we needed to check normality with a histogram or dot plot or something like that. All right, now let's talk about what this p-value is. When we did this one last week, I showed you, or I told you verbally, that what you would essentially do is the test statistic here was 2.76. And if you look that up in the table or with the normal distribution function on the calculator, you'll get back a probability. And if it's on the left, the probability is going to be as a probability should be. But if it's on the right, you got to subtract from 1 because of symmetry, or else it's going to be something like, I think, what was it? If you look that up, you got 0.0002. And so that was less than 0.05. So it passes on both ways. But let's just look at a little bit more about the p-value and how I looked it up. All right, so same test statistic that we calculated before, 2.76. All right. So that was X bar, because this thing was about those standardized tests. So it was 5.62. So that's pretty way out there. It was 2.76 standard deviations above the mean. So that was pretty strong. And as we saw by comparing the 2.76 to the 1 point, what was it? 1.96. No, the 1.645, we could see that it was clearly beyond that and in that critical region. So, as I had said is, and I'll just bring up the calculator here. What happened to the calculator? It was down here, like something took all my stuff off of here. It's like a bunch of stuff got deleted. What else going on? All right, I'll download it again. And do it. I was noticing yesterday that there was some files that I had downloaded this semester and they were gone, and now everything's going. So, all right, so let me, okay, so we're looking at 2.76, which you have to remember is the value that was calculated from the data, okay? All right, so we saw that 2.76 was beyond the 1.645, and so that's why we could reject the null hypothesis. But we're going to see that it can do the same thing if we're doing it with the p-value method. change it back to 0 and 1, because that's a z-value. Now here's the problem is, because that's from the right, then what we got to do is essentially do this. If it had been a left tail test, when we did that, we would have got the probability that we needed to compare. So I'm just going to subtract it from 1 and see there's what we call the p-value. It's 0.029 for essentially, or you could almost just round it off to 0.003. All right. So when they tell you that the p-value is 0.0029, they're showing you right there that the 2.76 has 0.0029 area to the right of it. Now, remember, this was the critical, what do they call it? The level of significance was 0.05, and since 0.0029 is less than 0.05, we reject the null hypothesis, which is the same conclusion if we do it by that other method. All right, so you just got to remember that the level of significance can change things. All right. So suppose that we got a p-value. In other words, we did our test and we came back with a p-value that was 0.0122. You could almost just look at those first two digits to help do this, but it's just a little bit more than 0.01 because it's got the 22 behind it. So at the 0.05 level, then we would reject the null hypothesis because 0.01 is less than 0.05. But if we had a higher level of significance, 0.01, then we would fail to reject because this is not greater than that. I'm sorry, it's not less than that. It's greater than that. So you got to watch. You'll have some like these where they'll have you calculate the test statistic, look up the p-value, and then affirm what would happen depending on what the level of significance is, and it can change. So as I had said is there's a strong correlation between hypothesis tests and confidence levels. So if you've got a two-tailed test, then the confidence interval basically gives you the n values to which to look. And so if your value for your test is outside of that confidence interval, you would know to reject. And so that's actually a third method of performing a test, but we don't look at it in this book, but it does mention this here. And we could kind of go from the, we had those same problem mentioned in both chapter 7, and then here as well about the boxes of cereal. And when we did the confidence intervals, the confidence interval had 20 inside. It was both of the n value and the upper and lower value were above 20. So it was safe to say there was not that there was 20 ounces of cereal in each one. And then also when we did the test for it. All right, but this is the more realistic example, and this is when we don't know sigma. So this is for when we gotta either calculate the sample standard deviation, or in a lot of cases they'll give it to you, but they'll tell you that's the sample standard deviation. Because if you had to calculate the sample standard deviation, it's a dead giveaway what method you're using. But if they give it to you and tell you it's a sample standard deviation, it's a temptation to just assume that it's the same value, but it's not. Okay. So here's an example. We've got a study with 76 students, and they're put on a low-fat diet, and then after a year or 12 months, the sample mean weight loss is 2.2 kilograms. And they tell you two ways. They say it's the sample mean, and they say X bar. So they're double telling you that that's not sigma. Oh, I'm sorry. I'll back up again. They're giving you X bar from the sample, and they're also here telling you that the sample standard deviation is 6.1, and they're also labeling it as S, which is a double indication that you don't have sigma, that you've got S. It's the sample standard deviation. It's S. So if we need a sample standard, does anybody else see me as frozen? I'm not frozen. Let's see. Let me see. I can see myself moving around on my other computer. Does anybody else see me frozen? So restart it. On yours, like if you do it on a browser, just hit the reload. Do it again. Because one of the reasons why I do two computers is so I can tell if there's a problem. Because on one, I got one computer here on the left. That's my Chrome box, and that's one that gets my video and audio. And then the Windows computer over here on the right is the one generally I do all the work with the mouse and switch back and forth for the different things you can see. And so I can see my voice on there, and I can also hear myself. So I can usually tell. But yeah, if it's me or not. Not always, but there's all kinds of things that can happen, with communication. All right, so if we knew the sigma, then we could just calculate the test value, like the Z, and then use the test statistic from the Z to perform the hypothesis test. But we don't usually know that, so we got to replace sigma with the sample standard deviation S, and then go to the T table instead. All right. And then the T table means you got to look up the n minus 1, in other words, the sample size minus 1. But the calculation is essentially the same. It's just the difference in the numerator is the difference between the X bar and the value you're testing divided by the standard error. And it's just a Z value. It's just that when you're doing it here, you're going to the T table. All right, so we've been given 2.2 and 6.1, and we'll just pretend that we calculated those. So since we had to calculate both of those, and that lets us know we got to go to that T table. So N is 76. So then we just fill in 2.2. And the null hypothesis is 0 because the status quo is the diet doesn't work, so you didn't lose any weight. The alternate hypothesis is that the weight was greater than 0. So 2.2 minus 0 divided by 6.1 divided by the square root of 76 gives us 3.144. Now that's a pretty high value for a Z-score. Now it's technically a T-score. So what we're going to do is, and I'll just show you on the calculator, they're telling you how they do it. But we got n minus 1, so 76 minus 1, so 75. So we're going to do it with just the plain old p-value here. All right, so it was, what was it? I forgot what it was. Pretty high one, 3.144. All right. So again, because this is a right tail test, see, you're getting what's to the left. We could have either switched those, or I'm going to do it like this. 1 minus. .001. So again, pretty small. And it's actually 0.012, okay? And that's what they rounded it to over here. So we reject the null hypothesis, that meaning that we reject the fact that this diet does not work because that p-value is smaller than 0.05. So we conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0 pounds, so that it worked. Now, hopefully you don't have to do too much of this because this is kind of a pain in the neck, but I'll just mention it. You can estimate a p-value from a table, because the problem with the table is you have these in between values. So in this case, it was the same thing, the 75 degrees of freedom. So you can't put in 75, you go down to 60, and then you go over to the ones here that are in green, which are the ones that are on the boundaries, because it was 3.144. So these are the boundaries of 3.144. So 3.144 is in between there somewhere. And what that means is so your p-value is in between 0.0025 and 0.001. And both of those are less than 0.05. So it gives you the same result. The tables are just kind of old-fashioned way to do it and not exact, but you can estimate in these kind of cases, because in both of those cases, it's not like it's a gray answer or something. It's definitely both of those values are in between. The in between values or the boundary values are less than 0.05. All right, so let's go through a whole kind of one where we look at the data and check it and everything, because we got a small sample here. It's talking about generic drugs. And before a generic drug can be sold in the US, it must be tested and found to perform equivalently to the brand name product. The US Food and Drug Administration is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredients to each square centimeter of skin. So when the ointment is put on there. So that's the mean, that's the X bar. As part of the testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed in the skin is measured, and here's those amounts in micrograms. So this is the what the brand name offers is 3.5. So that's what we're measuring against. Now, do it any kind of way you want. But let's see if we can put it in the calculator and do it. Because we need to have the X bar and the mean. But let's just go ahead. Well, they want us to use the level of 0.01 level of significance. But first of all, we just got to make sure that this is normally distributed, or so we don't, as long as there's no outliers. And it looks more or less even. You got the two that balance each other out there on the right and the left. There's no strong skewness, so we can assume that this is normally distributed. All right, so let's see if I can remember how to do this. I do this personally. For me, I would use the spreadsheet, but let's put it in here. So we got that's going to be on first. So clear everything out, and then we're going to put the values in there. $2.6. $3.2. So we got our values in there, the 8 values. So now, did I get all of them in there? Yeah. It's good. I have to always check them, because once you got them in there, you know, they're going to calculate for that. So now we just do stat, calcs, and then hit enter. And then that gives us the values we need right there. And they calculated them for us as well. But I wanted to just remind you how to do that. So we're measuring against the mu of 3.5, which is the brand name. And the question was, it was right here, how strong is the evidence that the mean amount differs from 3.5 milligrams? It doesn't say whether it's less than or greater than. So this is what we call a two-tailed test. So it's differs from. Differs from. All right, so it's a two-tailed test. So mu is it's equal to 3.5. Mu is it's not equal to 3.5, which is denoting the different from. So you compute in X bar and S, and that's what we came up with, the 2.9429. And then the sigma is 0.4995. That's the sample standard deviation. If you haven't figured it out, I'm going to point this out again. You got to watch out for this, because the calculator does not know whether what you're putting in there is a sample or a population. So it gives you both. All right. The one we want is S of X. So that's why the first one there is being used and not this one. Mean doesn't matter, because the mean is calculated for the same, whether it's a sample or a population. All right. So now let's just calculate the t statistic. And it's calculated the exact same way as the z statistic. We're just going to have to deal with the t table. So 2.949, 2.9429 minus the value we're testing. So this is our S. I'm sorry, our X bar minus the 3.5 divided by S divided by square root of N. So we've got now a negative value for a test statistic, negative 2.951. So you could estimate it, but I'm going to show you on the calculator. Now, the problem is you got to, because it's a two-tailed test, we got to do something at the end here. And I'll show you in a second. And it was 6 degrees of freedom. All right, now, oops, it wasn't showing. Let me show you. So the way that they're showing you on the table is that it's somewhere between 0.1 and 0.025. So then you have to double it because it's a two-tailed test. Well, I'm going to do that here on the calculator. So they just double the endpoints. The calculator makes a little bit more sense. And you're always able to use the calculator. So there's the value that comes back from just that negative endpoint, but we're going to say times 2. So there's our actual p-value, 0.026. All right, it looks like that's higher than our this value, but I mean than our level of significance. What was the yeah, it was 0.01. So we're going to fail to reject. So we do not reject because I'll just show you. Remember, it's 0.026. You could almost round it to 0.03 for the sake of this, but look at this. Like I said, they're specifically showing you how to do it with the table, but we're doing it exactly. So that p-value of 0.029 is greater than 0.01. So we're not going to reject. We fail to reject. There's not enough evidence. If they had a lower standard, in other words, if they had what was it, like 0.05 here, then we could reject it. And that was the same thing that they were kind of showing us up here, that depending on the level of significance, it will make a difference. All right, so all right, so the last section is the 8.4, and the last section is just a the same thing, or it's the test for proportions, and you just got to remember that the test statistic is going to be different because in chapter 7 we learned that there's a different standard error for proportions. because you don't have an X bar, you don't have a sigma. So we have the P times 1 minus P divided by N, square root of all that. So we have a simple, and the assumptions are slightly different. We have a central random sample. The population is at least 20 times as large as the sample. The items in the population are divided into two categories. The values N times P sub 0, that's N times the population proportion, and N times 1 minus the population proportion, both have to be greater than 10. So these two right here are the major ones. You got to divide the data into two categories, yes and no, true and false, black and white. And then you got to find out that the N times the proportion and N times the complement of the proportion are greater than 10 each, or at least 10. All right, so we want to test the proportion P of customers willing to purchase a new phone. In a survey of 650 customers, 286 replied yes, and 382 replied no to the question if they will buy a new Samsung Galaxy. This is like the company. I don't know what happened there. The company believes that more than 40% of these customers will purchase a new phone. All right, more than 40%. How would we proceed to test this claim from the above data? Now, this information right here is taken from the sample. So that's what's going to give us P hat, all right? That's X, N. So this is N. This is X. And this is not X. And so we can calculate P hat from that and 1 minus P hat, whatever we need from that. But that's the sample right there. Now, what the company is testing is 40%. We're going to test against 40%. So is there enough evidence to conclude that? Well, first of all, so this right here, what they call the P sub 0 thing, that's what we're testing against. See that? The proportion is equal to 0.4, and that would be the null. And what the company would like to prove is that it's greater than 40%, 0.4. Well, anyway, the assumptions are fine. We got two different categories, yes and no. But here's the one you always really, really need to check mathematically. 0.4 times 650 is 260. 1 minus 0.4 times 160, in other words, that's 0.6 times 650 is equal to 390. So both of those are greater than 10, or at least 10, so we're fine. Here's our hypotheses. So the P hat is 268, that's the yes category, over the total 650, which is equal to 0.41231. All right. So that's what we call the P hat. We're testing that against 0.4. You'll notice that it's greater than 0.4, but is it enough? Well, we got to do the calculation. So if we wanted to do this calculation on a calculator, let's just show you. See if I can have the patience to do this, because it's a but some people have asked me how to put things in the calculator, and with things like this, you got to use parentheses to do it. So it's 0.41231, which was the P hat. minus 0.4, close the parentheses. Now what we're going to divide by is that square root thing. And there's a square root button down there. All right. So you have to use the parentheses again, I think, here. Let's see. So 0.4 times 1 minus 0.4. And then all that's closed off. That's the numerator. And then what is it? It's divided by n, right? And if I did it right, then that should be the same thing. I may not need all of those parentheses, but I'm being safe. Because if you don't put in, for example, a parentheses over the numerator, around the numerator, then what happens is when you divide, since division occurs first, this right here is going to get divided, the 0.4 only, or the negative 0.4 gets divided by whatever you got down there. So you got to make sure you do that numerator as one operation and then divide it by the square root. All right, now that's a pretty low z-value, 0.641. And now remember, when you're dealing with proportion, it's always the z-values you're dealing with here. You don't have to worry about t-table or anything like that. So, what was the, oh yeah, use 0.05 level of significance. So for a right tail test, that's going back up here. .645 for a right tail test. If it had been a left tail test, then it's a negative. All right, so that's really less than one standard deviation. So that's not looking good, but let's just check it. All right. So the critical value for 0.05 is 1.645. And since that's less than this, we're going to fail to reject. This is the way they usually do it when they draw it out. They use the critical value method. But let's also do the lookup in the calculator. 0.641. So again, we got that, but remember it's a right tail test, so we got to do the 1 minus. If you get a huge value like that that's over 0.5, then that means that's an indication we didn't remember to do the 1 minus. So 0.26, really, really high. That's definitely greater than 0.05. So again, by both counts, we fail to reject. So there's not enough to reject the null hypothesis. So the company Okay, well, this is a left-handed test. I'll go through it just real quickly. Trials in an experiment with a polygraph include 96 results that include 23 cases of wrong results and 73 cases of correct results. Use a 0.05 level of significance to test the claim that such polygraph results are correct less than 80% of the time. So identify the null, the alternate, and the test statistic, the p-value, conclusion about the null hypothesis, and final conclusion that addresses the original claim. So use both methods. All right, so null hypothesis is we can conclude that the status quo, or 80% of the time, that the polygraph is right. The alternate hypothesis is that it's less than 80%. Okay. So we're going to compute the sample proportion, which is out of 96 cases, there were 23 wrong cases and 73 correct. So we're using 73 because we want to find the proportion that's correct. Say correct. All right. So 73 over 96 gives us 0.7604. And then we do our calculations with that, contrasting it against the 0.8. That's what we're testing it against. And then the standard error down in the denominator is 0.8 times 1 minus 0.8 divided by 96. So negative 0.97. So it's a bit less than one standard deviation, which I don't think that's looking good, but let's check. So this was 0.05 again. It's a left tail test, so the whole 0.05 is on the left-hand side, so we're using negative 1.645. Just like for the positive 0.04, the right-hand tail test, we had 0.05. We had a positive 1.645. So I should say greater. I don't know what I was. So it's greater than that, because you got to think of it. When it's a left tail test, you're just the opposite. So negative 1.645 is our line in the sand, and negative 0.97 is the value that we're going to find out which side of the line it's on. And it's on the right-hand side. For a left tail test, it needs to be smaller than negative 1.645. So again, we're going to fail to reject. Same thing, if you look up negative 0.970, and this one you don't need to put in the 1 minus, because it's a left tail test. Oops. So 0.166. Zero which is definitely higher than 0.05. So we fail to reject. So with the p-value method, you're not concerned whether it's negative or positive. You're doing it you're just comparing the probabilities. And if the probability of that particular value is less than your level of significance, then you reject. But if it's higher, then you fail to reject. So there's not enough evidence to reject the null hypothesis. So we can't state that less than 80% of polygraphs are accurate. So when we're on the left-hand side, like I said, everything is flip-flopped. But for the p-values, those are always going to be probabilities, and that you're measuring against that level of significance. It's just that when you're dealing with the right tail test, if you're looking up that test statistic there, you're going to bring back the complement, so you got to subtract from 1. For this one, it's going to come back exactly as you want it when you got that test statistic, because it's going to be negative on the left-hand side. For the two-tail test, whichever one comes back, it can be either negative or positive. But whichever one comes back, you got to double it. All right, so I'll just kind of briefly go through this and we'll get out of here a little bit early, I think. All right. All right, the final chapter is called Correlation and Regression. Now, what correlation and what correlation is, everything that we've looked at so far, we're looking at one column of data. What correlation and regression are is we deal with 2 columns of data, and the first thing we're going to find out is whether these things have a relationship that's consistent or not. It doesn't matter so much what the relationship is. It's just that, is there a significant correlation on these things? And one of the first things that we can do is have a scatter plot. And a scatter plot, and we'll see how to do these on an example come Thursday. But you could have a positive correlation, and notice that in real life, you're never going to have an exact straight line on data. But in the example here we're looking at, they're more or less clumped, so you can see that there's a positive correlation. And what that means is that X increases, Y also increases. The negative correlation is the opposite, and that is X increases, the Y comes down. And then if you've got things that are just all over the place and they're not in any kind of general either negative or positive relationship, then that's what we call no correlation. But the more important thing is the calculation, because that's going to be more precise. So when we come back on Thursday, we'll be able to finish this up. And before you get all weirded out about this, and we'll just do a small example by hand, but the calculator will do this in a snap. But all that is the z-score of the X times the z-score of the Y values, all multiplied together each, and then added up and divided by degrees of freedom. So like I said before, the z-score is the most important calculation in statistics, and that's what we're looking at here, except we're looking at 2 z-scores for every pair of data, and then they get multiplied times one another, and then summed up and divided by n-1. So we'll look at that on Thursday.